What's up, guys? Let's briefly discuss remote procedure calls and how they work. So, remote procedure calls. So, let's introduce this. API servers require enormous computing power to serve a large number of clients. In a distributed system, functionalities are divided into different subcomponents, distributing responsibilities to a set of independent working machines called microservices. Initially, people started building their own protocols and methods to communicate processes over the wire, which led to various customized protocols. And in the late 1970s, the Remote Procedure Call (RPC) architecture was introduced to manage and standardize the communication between two remote entities via a simple abstraction. RPC is not a new concept, it's a communication abstraction that enables remote code execution without worrying about the complexities of the underlying network. So let's learn what a modern RPC style looks like. So, what is an RPC? A remote procedure call (RPC) architecture is a service or action oriented style of creating APIs. So, where resources are distributed among different services running on remote machines, RPC facilitates inter-process communication by enabling clients to run remote procedures, functions in a simple local function call like abstraction, right? So looking at this picture we have our client stub, right? And right here, so this is the representation of the function in the client-side environment. It receives the function call from the client application, and which is packed into an RPC message and forwarded to the runtime RPC. So, yeah, it receives the function call from the client application, right? The client will make a function call, and it's packed into an RPC message forwarded to our runtime RPC. And then we have our runtime RPC, and here in our runtime RPC we have the IDL compilers, and IDL headers. And the IDL is an interface definition language, which is used to define functions at remote ends. The IDL compiler, it generates client and server-side compatible codes for client and server stubs. And the IDL header, it's a list of available functions that can be used by clients and servers, right? And then we have our server stub right here. And that is the representation of the function in the server-side environment. It receives the RPC message from the runtime RPC, which is unpacked into a server-side function call. So as you can see, we have a client-side stub, a server-side stub, and we have our runtime RPC in the middle. So the RPC runtime is the actual software program that does the heavy lifting and glues all the components together. It communicates with the underlying operating system and network interface to transfer data over the wire. RPC uses the interface definition language IDL to set up templates that specify function names, parameters, and so on, and to glue processes running in different development environments, right? So that's the point of our RPC runtime. So the IDL compiler runs only once, and it generates code stubs to support data conversion between different formats understood by programs written in different languages. RPC style APIs are easy to implement thanks to traditional function call like integration support provided by our IDL headers. And let's talk about some common RPC technologies for building APIs. So here we have a few modern implementations usually used in different kinds of APIs. The core of RPC is synchronous, but modern frameworks provide mechanisms to make asynchronous remote procedure calls to increase our throughput. So firstly, we have Thrift, and it's a software stack for generating cross-language and scalable services from interface definition languages. And we have gRPC, a framework for implementing RPC-based APIs using protocol buffers for serialization. We have RMI, Java to Java based object serialization library that uses RPC architecture for connecting to remote processes. And we also have SOAP, a protocol for implementing RPC based APIs that support structured data, namely XML, JSON for exchanging messages. This is becoming a legacy technology, while other new technologies like gRPC and others are gaining more traction. So how does RPC work? So it follows the request response model, and we can divide the request response cycle into 4 subsections. First, initializing the RPC calls from the client application, then packing data and forwarding to our RPC runtime, then establishing connections across the network, and lastly, transmitting data to the remote end through the network. And let's talk about our request and response. So before we discuss the request initialization, we need to understand the 2 IDL header types. We have an import module, a component added to the client side, specifying a list of functions it can call. And then we have our export module, a component added to the server side, specifying a list of functions it can perform, right? And the import and export modules defined in the IDL headers maintain a list of remote functions provided by the API along with the format of input parameters and returned data types, right? An RPC request is initiated by a client, and it must specify a function identifier and parameter list that are consistent with the signatures provided by the IDL import module, right? So here's an example. So we have an RPC available at this address or at this endpoint, example.com/RPC demo, and it accepts a single string parameter of a greeting, right? The request and response headers are sent and received by a JSON RPC client, and they are as follows, right? So here we have a request. The HTTP post request headers for the JSON RPC service are as follows. So here we have a post, here we have our endpoint, our version, and content type, and then here's our JSON. And this is what it looks like as our response, which is similar to HTTP, right? And let's talk about marshalling and unmarshalling data. So before a client or server can send or receive data, it must be converted into a format they can understand. Each client and server has its own stub responsible for transforming the request and response data in a mutually convertible format using the following techniques. So we have marshalling, which is packing data into a mutually convertible format. And then we have unmarshalling, unpacking data from a mutually convertible format. And both the client and server RPCs must agree on a common marshalling and unmarshalling technique during network propagation, right? Various values such as caller ID, service ID, parameters list, and so on that are required to make a successful RPC call are marshaled by code stubs, and trigger RPC runtime to transfer data over the network. So the overall process of communication demonstrating a complete RPC request and response cycle is shown here. So firstly, to introduce this is the RPC style of API communication, right? And first we initiate a request, right? Here we have our RPC client. It has the IDL import module here, right? And then we also have 3 different servers they all have their own IDL export module, right? So they all have a list of functions they can perform, and the client has a list of functions it can call, right? So first, it initiates the request, and then it marshals the data using the client stub here. And then it creates data packets using the client RPC, right? So it marshals here. It creates data packets using the client RPC. And it invokes the server-side procedure using the server RPC. And on the server side, it unmarshals the data using the server stub right here. And it returns a response after necessary processing by the server. So the server gives a response. And it marshals the returned result using the server stub, right? So after you get a response, it'll marshal it again. And then it creates a data packet using the server RPC. So the server has an RPC after it marshals it. And it transmits data via the network protocol, of course. And it returns the response using the client RPC. So it goes through the client RPC then. And then it unmarshals the result using the client stub, right? So it unmarshals on the client side. So you can kind of see how it works. So it kind of marshals, goes through the client RPC, goes through the network protocol, and then it ends up at the server RPC, unmarshals, goes through the server for processing, and that process is sort of reversed. So let's talk about binding connection. Client and server communication starts by establishing a connection via a method called bind. There are 2 types of binding in RPC. There's static binding. The server endpoint IP address and port is dedicated and already known by the client. And then you have dynamic binding. The server endpoint is already decided and assigned by the RPC dynamically using a DNS resolver. Each client and server has its own runtime RPC responsible for reliable communication between them. It packs data into chunks that can be transmitted over the network. It also specifies the network protocol used for communication and handles network-related problems. Most RPC protocols come with rules that exhibit high performance by fine-tuning transport and application layers. RPC can work with transport protocols like TCP and UDP, though popular RPC standards such as gRPC, JSON, RPC, SOAP, they all use HTTP. So that's TCP in most cases, but for HTTP 3.0, it uses UDP. And let's talk about the advantages of RPC. So the RPC architecture has the following key properties that make it a desirable choice for working with distributed systems such as microservices. RPC is operation-oriented. That means we can easily add endpoints when the API has new requirements. RPC provides significant network abstraction, making it easy to implement without worrying about the network details. RPC-based architectures such as gRPC led to better performance and are easier to integrate because of the IDL modules They allow for automatic code generation for popular languages. RPC architectures also allow faster development with libraries supporting most of the popular languages. And some of the disadvantages are changes must be reflected on both the client and server side, making it harder to update, right? Custom stub libraries may have to be created for some languages, and if a language of our choice is not supported by a specific IDL compiler, we might need to change the strategy. So, how does a server know that there's a particular request intended for it? So, we can identify a server directly by its IP and port number in a statically established connection, but for a dynamically established connection, the name and the directory information set by the RPC runtime determines the intended server for a particular request. So, in summary, what did we learn in this lesson? We looked at the different components involved in the RPC architecture. We learned how RPC abstracts away the underlying complex network details, and we will return to RPC style later when we discuss the modern framework gRPC for developing RPC-based APIs. So hopefully you learned something, and thanks for watching.